C oxidase. One at a time. And they're transferred one at a time to oxygen. And oxygen, when O2 molecule receives, it needs 4 electrons, okay, plus 4 protons to make 2 molecules of water. But it delivers electrons, and that's what cytochrome, this complex 4 is called cytochrome oxidase. This is what transfers the electrons to oxygen to make water. But it does it one at a time. Now if you add 1 electron to an oxygen molecule, do you know what you produce? Something called if you have an imbalance of electrons, those are extremely reactive molecules. They're called sometimes free radicals, and they're very dangerous. Free radicals cause tremendous cellular damage. A lot of mutagenic agents are essentially free radicals. They have an unbalanced electron charge, and they love to destroy things like membranes and DNA. Okay? So if the cell, and since the electrons are transferred singly here before they are added to oxygen, if 1 electron was added to oxygen, it was let go, that would cause tremendous cellular damage. That wouldn't work. Okay? So what happens is that oxygen is receiving the electrons one at a time. It's held, it's in a pincher between an iron and a copper atom. It cannot leave. And it receives 1 electron, then the second, third, the fourth. Protons are attracted because of negative charge, then it lets it go. So there's a trap, there's an iron-copper trap in this last complex to stabilize that oxygen until it receives all the electrons and the protons to balance the charge. to reduce the spread of free radicals that could cause cellular damage. Okay? Very important. Here's another kind of view of this is a simpler view of that. Okay? This is complex 1. They're not showing complex 2 here, where FADH delivers this electrons further down the hill. But here's an ADH delivering 2 electrons. It's oxidized back in AD. Plus now it can participate again in the Krebs cycle. Okay? Those 2 electrons, as they are transferred through a series of flavin mononucleotides and iron sulfur complexes, it results in 4 protons being pumped here. It then moves through a lipid transporter, completely fat soluble in the membrane here called ubiquinone, delivering those 2 electrons to the second complex, in this case 1, 2, 3, cytochrome C reductase. I won't ask you to know these names either. Okay? As the 2 electrons flow through here, it pumps another 4 protons here. Okay, remember now FADH not shown to deliver electrons to complex 2 here. As they flow through here, another 4 protons pump this way. And then it's delivered via cytochrome C, the cytochrome C oxidase. This is where the electrons are delivered now. Here they're delivered in 2s, and here they're delivered 1 at a time to the oxygen molecule that's pinched between iron and copper, so it cannot, with an imbalance of electrons, cause cellular damage. It's pinchered there until 4 electrons are delivered, 4 protons to make 2 molecules of water. They're showing you half the reaction. Okay? And of course, this is when hydrogen is at its lowest energy. Okay? And again, 2 protons are pumped. So for NADH, 4 protons, 4, 2, 4, and 4, 2 is 10. 10 protons pumped for the 2 electrons for NADH. Okay? Since it takes 4 protons on average to spin through the rotor, not shown, in NADH, those 2 electrons yields 2.5 ATP. Well, pretty gnarly, huh? You think about changing measure? You're down. Okay. I like this schematic. This is from the Molecular Biology of the Cell. I love that book. It kind of gives you a kind of a crude schematic of how electrons from the membrane can function as a proton pump. Okay? And again, when you think about it, it's really the electrons flowing through the transport chain. It's an electric current. I mean, it's an electric current for sure. And think of these as proton pumps. If you've got a pump, like a water pump, like when my house flooded 2 weeks ago, I had to buy a shop vac, and I took over 100 gallons out of my basement. Okay, plugged that once the power came back on. So these are not water pumps; they're proton pumps. But like my shop vac, it doesn't work unless I plug it in. I hate that. Okay, these don't pump unless there's a current flowing through it, right? So they're like electric motors. And it sort of works like this. When the electron is passed from one transport protein to another, of course, the negative charge attracts a proton to neutralize the charge. Then the electrons pass the other, the proton just gets released to the other side of the membrane. Easy. So there's a port way for the proton to enter this proton on this side, or there's a port way on this protein for the proton to be attracted to the negative charge of the electron here. Now it's neutral, opposite charge attraction. And then the electron sent onward, it's kind of a one-way channel. The proton is released, and it is not allowed to follow the electron, and it just released on this side, so it crosses the membrane. Pretty cool. Does that make sense? You guys play poker? Don't ever play with me. Now, why do these electrons go through these electron transport components? Well, it's explained by this graph figure from your textbook. If you look at the protein, the electron transport complex in the inner membrane of the mitochondrion, and you graph them on a y-axis that shows you the free energy relative to oxygen, they're going to say oxygen. They're going to use this as zero, just as a comparison here. You see that NADH is at very high free energy. Okay, it's those high energy electrons make it. There's a lot of usable energy there. That's what free energy is. It's very high energy, which makes it very unstable. Which means it readily wants to give those electrons away. Things that have a lot of free energy are unstable, and they tend to fall apart. Things that have very low energy, they're very stable. They don't like to give their electrons away. Once electrons combine with oxygen to make water, boy, they're hell to get rid of. I mean, it's like trying to take a buck out of Trump's hand. You're not going to get it. Give me that son of a bitch. High energy is unstable. The electrons are readily let go. And they flow down this free energy gradient. Remember we said, if you remember we looked at delta G, that equation, the change. We looked at the free energy exchange and a reaction is equal to the change in potential energy minus the change in entropy. As long as delta G was negative, or less than zero, it was a spontaneous reaction, right? Look at the change in delta G, electrons flow downhill. It's a reduction in free energy, it's a spontaneous event. It's a negative delta G, it's going to happen. Don't need to push, just let the electrons go. They're unstable, their electrons are attracted to these lower free energy substances, and they just go. And these are all the metal complexes. These are, again, iron-based here, iron sulfur. These are iron heme units. The way the iron's held in these cytochromes is just the way it's held like in hemoglobin. It's an iron held in what's called a porphyrin ring. And then down here, part of this is that iron-copper complex to hold the electrons one at a time before they deliver to oxygen to make water. Okay. Another way to view this spontaneous flow is to look at their redox potential in millivolts. Okay. Things that have a negative. Now these are actual measurements you can make. You can take like NADH and ND plus put them in equal molar concentration in a fluid, compare them to a standard. You can measure their redox potential. These are actual measurements. Okay, and you can see the more negative the redox potential is, the less stable you are, the more likely you are an electron donor. You want to give them away because you're high energy and unstable. When your redox potential is positive, it means you're a good recipient. You can hold on to them real tight. And that's the bottom of this chain here. So these elements with negative redox potentials want to give electrons away. These want to hold them. And this is really the actual measurement of free energy. Notice the free energy decreases here. If you look through these three main complexes, complexes 1, 3, and 4, notice how it's real steep to the complex. It kind of flattens out real steep here. So the electrons travel these complexes, they fall in energy really fast. Okay? Why would life build this very complex system to harvest energy? Why not just have the electrons delivered to oxygen right away and skip all this cascade? Why not just let them fall right to oxygen and harvest the energy that way? Why can the cell not do that? Why not? Why do they have to kind of stair-step down? There's a fall, then they kind of stair-step and fall and stair-step. Why not just let them go right to oxygen. Because the amount of energy released will be the same, be that much energy. So why go through all the trouble of having this very complex pathway? What is the point of that? Anybody answer the question? Let me show you the slide that early in this lecture, actually on Monday, is the answer. If a cell were to let these high energy electrons go right to oxygen, that energy would be released instantaneously as an explosion. Not good for the cell. Okay? But if they're allowed to cascade down step by step through like this electron transport chain, the energy can be released in packets, okay, and harvested. Okay? So the bottom line here is these electrons move through this electron transport chain spontaneously because the delta G is negative. And that at this part of the scale here, these components of the electron transport chain have negative redox potentials, mean they're unstable. They tend to be electron donors, and as their redox potential increases, they tend to be more stable electron recipients. They hold on to them real tight. Okay? So that cascade of electrons, the electron transport chain, remember what it does is it energizes those complexes that function as proton pumps to build this proton gradient. Here's the intermembrane space. This is in the